Hey, what's up, guys? Yeah, so today I want to talk about another analytic number theory. Now some number theory results related to partition, which is a so-called Jacobi Triple identity. Okay, so let me just write down the theorem and I'll give the application and I give the proof. Hope you guys subscribe to my channel. Okay, so let's say x belongs to a complex number and z is a complex number and x is less than 1 and z is non-zero. We have n from if you go to n from product 1 to infinity, 1 minus x to n, 1 minus 1 plus x to n minus 1 z square, and 1 plus x to n minus 1 z negative square will be summation n from 1 to infinity x m square z to m. Okay. Okay, so now let's see the applications. Okay, so simple applications. Okay, so maybe let me just doing a stupid thing. Let me just copy this. So 2n 1 plus x 2n minus 1 z square 1 plus x 2n minus 1 z negative square will be summation n from minus infinity to infinity. Sorry, this is, I forget about this. This is minus infinity to infinity. Xm square z to m. Okay, so simple application. Let's say I define x to xa and the z square to be x b, but there's a negative sign. Let me just do the simple replacement. Then I will get the following. I will get the n from 0 to infinity 1 minus x to na 1 plus x 1 plus x 2na minus a plus b, and the 1 plus x 2na minus a minus b will be n from negative infinity to infinity x am square plus bm. Okay, so it's very simple. So let's let a to be 2/3. Sorry, 3 divided by 2. I mean 2/2, right? Sorry, not 2/3. 3 divided by 2 and a half. Okay, then I will get n from 1 to infinity 1 minus x 3n 1 minus x 3n minus 1. You can see that this is minus 1 and the 1 minus x 3n minus 2. Okay, and you might see, oh, what is this, right? If you plug n from and go to 1, you get 1 minus x cubed 1 minus x squared 1 minus x, and n is equals to 2, you get 1 minus x6 1 minus x5 1 minus x4. Okay, so you can easily see that this guy just n from 1 to infinity 1 minus x n. Okay, equals to summation n from negative infinity to infinity x 3m squared divided by 2 plus m divided by 2. Okay, so this is just, you do the inverse of the generating function of partition and then you get the pentagon number. So this is exactly the Euler pentagonal number theorem, which is previously I used the combinatorics, or you can use combinatorics or you use other method to prove. Okay, so this is a very simple application. Okay, another application, that the second application is also famous, called the cube of the Euler product. Okay, so it looks like following, right? You go to n from 1 to infinity 1 minus x n to the cube will give you this infinity to infinity and 1 minus m x m plus 1 divided by 2. Okay, yeah, okay, and this is exactly the same, right? You can flip it, you can combine the even and odd parts, so you get m from 0 to infinity minus 1 to m and then times 2 to mx, not 2mx, so it's 2m and plus 1. Let me just write down 2m plus 1x m squared plus m divided by 2. Okay, so proof is very simple. You just replace z squared to minus zx. Okay, so you can see that you get n from 1 to infinity, 1 minus x to n, and the 1 minus x to n z, 1 minus x to n minus 2 z inverse. You get n from 0 to infinity, minus 1m, x m squared plus m, and the z m minus z negative m minus 1. Okay, so now you can do this, right? You just do let's see. Okay, so first you notice these terms, right? These terms can be written as a n from 1 to infinity, 1 minus x to n z minus 1. So you can take out one term, right? That you can take out 1 minus the inverse one term, right? Because when n goes from 0, you get this term, right? So you just add this term. Okay, then you can write this in terms of 1 minus the negative inverse, and the 1 plus the minus 1 of the z up to negative 2m, and the times z to the m. Okay, so you get this. You got this. Okay, so now you can just cancel. Okay, so let's cancel. Okay, so we can cancel these two. Okay, so once you cancel these two, you get this one up to this one, and this one. Okay, then you just take z to be 1. Okay, when you take z to be 1, then you get 1 minus x to n, 1 minus x to n, 1 minus x to n z inverse, which is 1, right? So you get 1, 1. So this becomes n from 1 to infinity, 1 minus x n to the cube, equals to the right hand side, which is n from 0 to infinity, minus 1 to the m. So x m squared plus m still the same. And for this one, yeah, so for this one that you get you also need to replace x to square root of x, because this is 1 minus x to n, so you get this. So this one you need to divide by 2, and for this one you are going 1 2m, right? So there are 2m minus plus 1 term, because this is 1 plus z inverse up to z to m. Okay, so that's it. So you finally just replace x to a square root of x, then you get this cube of Euler products. It's not difficult, just calculation a little bit tedious. Okay, so now talking after the application, and what we should do, we should start to prove. Right? We should start to prove this theorem. Okay, so proof. Okay, so this is the proof is not so simple, but let's go step by step. I mean, it's interesting. Okay. Okay, so let me just forget about the property of the convergence. I mean, you need to check the convergence by yourself. I think it's not difficult. Okay, so you can get f of z to be let's say n from 0 to infinity, 1 plus x to n minus 1 z squared, and 1 plus x to n minus 1 z negative squared. Okay, so lemma. So you can see this is the part of the left hand side. Okay, so let's check. So lemma is that xz squared times f of xz is f of z. Okay, so this lemma check is not difficult, so I just skip. You can prove by yourself. This is very simple. You just try to use. You just try to use xz squared equals to 1 plus xz squared divided by 1 plus x inverse z negative 2. Yeah, this is trivial. You can see that you times this, you get this. Okay, so this is trivial, and then you just write everything down. Trivial. Okay. So let's lemma just this. Let g of z to be f of z times summation n from 1 to infinity, 1 minus x to n. Oh, this is already the left hand side of Jacobi triple identity. So all I need to show is this. This is what I need to show. I need to prove this part is correct. I need to prove that this part is x m squared z to m. Okay, so if I can prove this, then everything will be trivial. Okay, so I can do the round expansion. So I do a round expansion on a m z to m. So let's say I do the expansion. Because this is mo z squared, right? So I can use a z squared as an analytic, and I expand it. Okay, and also I can see that am is a negative m, because z squared is the same, right? I mean, because this is the same. And also because and the GZ is basically this is the same as GZ as GZ inverse one. Inverse. Okay. So you can once you have this and then with this relation, okay, you can easily prove. Okay, so let me just write down, right? So you can use this. You can use this equation 5. You can use this equation and with this expansion and prove the following. So let me just write down. This proof is also not difficult. Combine these two, you can show that am is x 2m minus 1 am minus 1. This is just a simple calculation. You just expand it. You just expanded your power series and then expanded it. Okay. Okay, so let me just write down. Let me just go to the next page. Okay, so what we have is this am is equals to x2m minus 1 am a0 xm squared for all m greater or equal to 0. Okay, and also you can check that m less than 0 is correct. This is just very simple. This is just you. Oh, sorry, 1 plus 3 plus 5. Sorry, 1 plus 3 plus 5 up to 2m minus 1 is m squared. We just use, well, we just need to use this. Okay, so now one can write my original g. Okay, so that means remember that our g of z in terms of is am z to m. Okay, and I got then I already get this answers, right? I already get these answers, so I can plug it in, and I will get exactly get some results which only depends on one number. Okay, so I will get the exact results. I will get a0 of x, because you remember a0 may still depend on x, and m from negative infinity to infinity, x m squared z to m. Okay, so the remaining is to show what? Remaining is to show that this guy is 1. Okay, this is our final goal. Okay, sorry. Okay. Okay, so okay. So I want to claim that this a0x is 1. They do not depend on x. So our goal is a0x is 1 for every x. Okay, this is very weird, non-trivial to prove. But so one way is just doing that's right. So let's write g, and the right compute is with exponential pi I divided by 4. Okay. This is very weird that why this is true. Okay, so let's try to see this. And yeah, so this is z. Okay, so I use z. Okay, if you do this, then you get you get a 0 x m from negative infinity to infinity x m squared I m. Okay, it equals to also equals to n from negative infinity to infinity minus 1 to n x to n squared. Okay, so this is definition, and for this one you just see that I m is a negative I negative m if m is odd. Okay. Okay, so basically you get the following. You get the you get the g exponential I pi divided by 4 divided by a0 of x is this. Okay, and then you can check that g exponential I pi divided by 4 divided by a0 of x is exactly the same as g if you right, because this is right. If you can see that this is, let me just write down. Because it's 2n squared, right? So it's 2n squared, so I can do g of I. This is just a0 of x4. Okay, this is weird, right? Because now that means that if you okay, so combine okay, so you see this, right? So for this one, you get this. Okay, if you replace it by I, then you can just do x cubed. Sorry, you can do x4. The reason is that, or remember that our g is divided by a0 of x, summation n from negative infinity to infinity, so x m squared plus z to m. So if I replace z to be I, then in order to compensate this, to make this expression still the same, I need to replace x to x cubed, this x4, right? So I can just do this. Because I will get additional 4 term, I just pull it out. Okay. And remember that the g of this g I pi divided by 4 is what? It's hard. Okay, so we have this, right? But the weird thing that I'm going to prove is that okay, so there is a final lemma. Final lemma is that actually your g exponential I pi divided by 4 is exactly the same as g of I. Okay, so the reason is that this guy is the same as n from 1 to infinity, 1 minus x to n, 1 plus x 4 minus 2. You can just write down a definition. Remember this g is remember this g. Let me just, yeah, I mean you just plug in by your definition, and you can see that you can see that this this is definition, and then you can see the following, right? If you go to n from 1 to infinity and then go to 1 minus x to n, and each number in the odd, each number either even must be 4n or 4n minus 2 form. So you can run n from 1 to infinity 1 minus x to n to be n from 1 to infinity 1 minus x4n and 1 minus x4n minus 2. Okay. So which means that you can just replace this guy to be n from 1 to infinity 1 minus x4n, 1 minus x4n minus 2, 1 plus x4n minus 2. Okay. So what? So you can combine, right? You can combine what? You can fix this and combine these two. Right, you can combine these two, so you get n from 1 to infinity 1 minus x4n. Let me just change the color, so because this space is very beautiful, so 1 minus xan minus 4. Okay, and you can just replace this to be n from 1 to infinity. You do exactly the same thing, 1 minus xan and 1 minus xan minus 4, right? Because each 4n number, each 4 number which is 4n is just basically an or an minus 4. Okay, because each number divisible by 4 is either divisible by 8 or multiple of 8 minus 4. So you get these three terms, which is you did this return combination, right? You get these three terms products, and then you can check that this is just this. Okay. Okay, so combine these two, we can cancel this. So for our final result is a0x is the same as a0x4. Okay, and then you can do this and prove that this is a0x16, right? And a0x64. Okay, so you prove that a0x is basically a0x 4k. Okay, 4 to the power k. Okay, but I know that x forced to the power k goes to 1, right? Because my definition is my definition is that this x is less than my definition is that my definition is that this x, right? So I can, if I let k to be infinity, then this x forced to the power k will less than 1. Okay, so which means what? So which means that your a0 x will goes to 1 as x goes to 0. Okay. Okay, and so the final thing, maybe you need to worry is why I know that a0x should go to 1, right? Why a0x should go to constant, but why 1? Why 1, right? I mean, you go back, you can go back to here, you can go back to original triple identity, and you can assume that maybe there is a constant here, let's say a0, and you can just do the expansion of x, and you can see that a0 should be 1. That's it. Okay. But in our proof that we prove is constant, so you just plug in, you can just maybe replace x to close to 0, right? And then you get a0 should be 1. Or you just expansion and do the longest term for x. Okay, so yeah, so this is the proof of this Euler, this Jacobi triple identity, and I hope you guys subscribe to my channel. Thanks.